My name is Stefano Torressi, and I'm going to talk about continuous integration and delivery and deployment. So, first of all, a quick primer. I suppose that most of you already know these things, but what are continuous integration, delivery, and deployment? Basically, they are a set of practices, software engineering practices, where that incrementally aim to achieve a set of benefits that can enhance the productivity of an entire team of developers. And the first of these practices is to the ability to merge developer changes continuously on a main line. That means that instead of having the concept of difficulties during integration of many changes of many different developers, we aim to merge these changes very often multiple times each day. And this comes with also with a set of automations, most prominently the testing automations. In fact, continuous integration was born basically along the rise of TDD, and it makes basically integrating changes easier, and it avoids the so-called integration hell. And the next step after continuous integration, which allows you to put all the changes into a single mainline, which by the way, it's basically usually the master branch of your Git repository. Once a long time ago, it was the trunk of an SVN repo. And the next step is continuous delivery. And continuous delivery is basically the concept of keeping this mainline branch in a production ready state, so that you can always deploy it to production. Every time something gets integrated, it must work. You can't integrate work in progress stuff. And the next, the step further, and the final step is continuous deployment, where while in continuous delivery, the deployment of the production ready branch is done manually, usually. In continuous deployment, we have an automation for that too. So basically, every time a developer submits a change in the central repository, it automatically gets deployed in production after, of course, a series of steps. And why do we want to do this? Why do we want to do this? We can use this to enforce a set of practices. For example, we can enforce code quality, and we can enforce having tests. We can enforce code styles. We can enforce static analysis. And via static analysis, we can gather metrics. And all of this has the very nice effect of granting confidence and a sense of safety to your teams, because there is no more the concept of you don't deploy Friday evening, for example, because everything is always ready to be deployed. And if something goes wrong, the continuous integration pipeline, so-called, so these steps of automated checks will protect you from making mistakes. And this is also because you tend to minimize the manual interaction. So the deployment is no longer something that involves human mistakes. And this also fosters collaboration between people, because you have a much shorter feedback cycle. So every time you push a change, you very quickly know if the change breaks something, and you can everything is visible. One of the tenets of continuous integration is that the process must be visible to every collaborator, so everybody can cooperate when something goes wrong. And as I said, you can also collect interesting metrics. So you can, for example, collect code coverage, or the number of lines of code per language, or some kind of stuff. You can basically make your own metrics at that point. And this whole concept goes along with the mantra of release early, release often, which is something that you may remember of being advocated for by Eric S. Raymond in his essay The Cathedral and the Bazaar, which is a very old essay about software engineering and specifically about Linux kernel development. And how do we achieve this? Basically, I don't know why it always skips one slide. How do we achieve this? Basically, we have to implement a pipeline of automated steps, and this pipeline usually is divided in stages. For example, we may have a build stage where we compile our code or install dependencies, etc., and we may package it. And usually nowadays you package it as a Docker image and create this Docker image and push it in some registry. Then we have the test stage where we actually run the image against different kind of test suites. And once this, the concept is that you don't go in the subsequent stage unless all the stages before have passed. So in this example, we want to achieve the deploy stage where we automatically deploy to a staging environment if any of the test jobs has failed. And as you may notice in the deploy stage here, we have two jobs, and one is automatically done the staging deploy, and one has a little play button, and that little play button basically means that in this case we're implementing both continuous delivery and continuous deployment, where continuous deployment is targeted against a staging environment, so we don't risk to break the production environment with automated deploys, and the production deployment all it needs basically it's a one-click operation, and once we can validate manually that the staging environment is okay and it achieves what we want to achieve, we can deploy it to production. So let's kickstart a project. So I show you how to start something like a basic Docker hello world, okay? Hang on a minute. Okay, here we are. Okay, so I'm gonna just make a directory and let's call it demo, and let's just start with a basic Dockerfile. This is very round of the mill stuff for you probably. So I'm going to use PHP because why not? And after all, I have a lot of paths with PHP, and PHP is easy because we can just copy an index.php to the document root. And our very complex application, as you can imagine, is going to print hello world. Okay, so once I have this Docker image, the next thing I want to do is to automatically build it. And one way to achieve this is to use a continuous integration software as a service or a platform as a service. And in this example, I'm going to use GitLab. GitLab is basically, as you may know, as Git, but it also has a continuous integration service, and it provides you free workers for your continuous integration pipelines. And as many other services like it, it basically works by committing a YAM file, which is a manifest of the configuration that the worker must use. And this is, again, as we saw earlier, structured in stages. So we want first to declare our stages, and we have a build stage. And then we define the jobs for each stage. So we're gonna just call our first job build up, and this goes in the stage build. And the interesting thing here is that we can use, basically with GitLab CLI, we can use any Docker image to run our images, to run our pipeline. So we can define as image, for instance, the Docker image itself, and we can define services to run alongside this Docker image. And what we're going to do here is to run Docker in Docker to allow us to build the images and then run them. And after we declare this service, and we need to define a special environment variables for this to work, which is Docker host, and it should be TCP Docker 2375, if I'm not wrong. Let me check for a minute. Yep. And then we have a script element in this YAML, and this is basically gets compiled into a bash script, and then the Docker image, the image that we define here, will run the script inside it. So what we want to do for the time being is just build the image and then push it to the registry. And GitLab CLI and GitLab in general also gives you a Docker registry. So I'm gonna build the image and tag it, and here we have to we can leverage some automatically generated environment variables for the CI environment, which always start with CI underscore, and it automatically defines a registry image name for us, which corresponds to the repository name and the user. It's basically an interpolation of many different things. And we're gonna use the commit short JSON as an image tag, and we'll get to this later, why this is a good idea. If you remember, Docker best practices discourage to use floating tags like latest, so we're going to use specific commit SHAs to reference images, and we're also going to use we're going to tag it twice. Let's put this in the new line. I'm gonna use 2 tags for this, because we also can tag, we can have a floating tag, which is not latest, and we can use a commit ref slug, which is automatically generated for us by GitLab, and basically it points to the branch name, and it is slugified, so it strips strange characters from it. So for instance, if you have a branch name with slashes, it substitutes the slashes with dashes, and this will come handy later. I'll explain why. And after we build it, we have to push it to a registry. So I'm gonna have to log into the Docker registry in GitLab, and we can do that with a special user that GitLab provides you. And we're going to use a special token. So this is very, there is a bit of boilerplate, but it's easy enough. And most of other CI services don't actually make it this easy. And then we push the image after we log in, because we log in because the image will be public, but we need the right access to push it, obviously. And I'm gonna push it with the very specific tag. Okay. Now let me check real quick if GitLab CI has a linter that allows you to validate the CI configuration, so you don't make it go wrong. And so I'm gonna just copy this to my clipboard and check it. And in the meanwhile, I'm just gonna git init, git remote, add a remote, and git add. Non lo vedete? Ah, scusate. Eccolo qua. Mi è scappato un tab. Okay, and so we push it, and this should already be triggering a CI run. So let's see if we can see it. It's a bit zoomed out. I don't know why. Probably because of the IDPI resolution. With a variables config should be hash key, or okay, let's fix it. This is hash. Let's get back in our project, and we should have a pipeline running. Yep, and this is our first job. It built the image, and it pushed to the registry. And if you go to the registry, you should be able to find the image here. Now there will be a bunch of other images because I did some tests before, but this is the image I just pushed, and the tag is the commit, the git commit. Okay, so the next step is to add some tests, because there is no CI without tests. If you don't have tests, you're not doing it properly, and we just have to add some jobs for this. So we're gonna add test phase, a test stage, and we're gonna add a test job. We're still gonna use Docker in Docker, and we're gonna copy all of this. And our script now is just going to run the image, and demonize it. Then we're gonna grab the output with a shell script, and we're gonna use, let's give it a name. And we're gonna exec curl in it. So this is our actual output, and we're gonna expect that the output should be equal to hello world. And if it doesn't happen, then I'm gonna just output the actual output, and fail the whole pipeline with an exit one. Okay. Let's see if we did the YAM properly. Okay, as you can see now the pipeline has a new stage, and it's going to run as soon as the build is finished. The provided runners for GitLab CLI for the free version are a bit slow, but you can easily run actually the GitLab CLI runner agent, which basically it's nothing more than something that listens for Git hooks and launches this container. And you can run it on premise and on your own cloud or everywhere you want. It's very easy to set up actually, and it's all very well documented. So I encourage you to give it a try. Here is the test running. It's going to pull the image from the registry. One way to speed up the build, and continuous integration usually implies that your builds must be quite fast, because it actually failed, I think. Let's see. Text not found. Oh, because it's test, a typo. Exactly. Okay, and while we wait, as I was saying, the continuous integration pipeline should be as fast as possible. And once we have completed this phase, the test phase, the next thing you want to do is to have somewhere to deploy this Docker image. And this is where obviously Kubernetes kicks in. And so just to know a quick show, and how many of you use Kubernetes in production? Okay, quite a few of you. So I'm going to go over this real quick. Kubernetes, as you may know, is basically not even anymore just a container orchestrator, because you can call it a platform, basically. And it abstracts infrastructure, and it automates and coordination of many different containers. And it also allows you to manage the whole infrastructure abstractions. And it's API driven. So if we look at how it is designed, it is very cluster centric. So it has the concept of a Kubernetes control plane. The control plane is a master node, usually even more than one, but high availability setups are a bit more difficult to implement. And the master has a bunch of components running into it. The main one is the API server, which acts as the main UI, and it is a very flexible API and very transparent. There are no hidden technical details, so you basically can do everything via this via this API server. And the way it works, it basically provides you with a declarative API. You declare what you want, and it takes care of matching its internal state with what you declared. And its internal state is stored into an etcd cluster. And there are other components, specifically controller managers. There are quite a few of them, and you can even roll up your own. And there is the scheduler. And what the master does is basically it interacts with the worker nodes, also called minions. And these worker nodes have a couple of components inside them. The main one is kubelet, which is a main agent that communicates back with the master and communicates its state. So the master can schedule the things that you want and can match your desired state. So for example, you can connect to the API server and say, okay, Kubernetes, give me 5 replicas of this deployment. And until there are 5 replicas working, the API server with the controller manager and the inner workings of the master will communicate with the various nodes until it has 5 replicas of what you asked available to you. And there are also very interesting cloud integrations implemented by the cloud controller manager, which allows you to offload some of the details, the technical details, to your cloud infrastructure. So if you want to, for instance, configure edge networking or routing or ingresses, usually do this by deploying workloads outside your cluster, but in a cloud environment. And there are quite a few of those. So can I have a cluster then? And it's not that easy. There is certainly a very high cognitive load, a very high, very steep learning curve. Operating the control plane in particular is very hard, and it's very hard to. There are a bunch of different ways to set it up, and there is special care to be taken for the high availability setups. And basically, you don't want to do this. Unless your job is, your business is to operate Kubernetes cluster, you don't want to operate a Kubernetes cluster. If you just care about your applications and you just want to run containers somewhere because you need somewhere to run your containers, then you probably don't want to operate a Kubernetes control plane. And there are also a few open questions, specifically multi-tenancy, which is still a work in progress. So basically, the whole model of tenancy in Kubernetes is very soft, meaning that multiple tenants inside the same cluster are not very hardly isolated. They are isolated, but to some degree. And this is called basically soft multi-tenancy. And there is a very quick way around this, which is basically you want to have a Kubernetes cluster for each of your tenants. And this is also why you don't want to run a Kubernetes control plane. And this is why the whole idea of Kubernetes as a service comes to rescue. So every major cloud provider, Azure, Google, AWS, DigitalOcean, IBM, all of them have Kubernetes services. We have all the case. So they all expose a very simple CLI SDK usually, and you can set up a cluster with just a CLI command once you have an account. So we're just going to do that. So I already have my disclaimer, I'm not affiliated with DigitalOcean in any way, but I have their API already configured. So what I'm going to do is to create a new cluster for my hello world. And what it needs to do, what it needs is probably a zone, a deployment zone. Let me check it. A region. I'm going to use Frankfurt, and I'm going to tell it to spin up 2 nodes, 2 worker nodes. And it's cluster create. I'm going to wait for it to, this is going to take just a couple of minutes. And while we wait for the deployment, and we're going to take a look at the various different workloads that you can use, the various different APIs. There are a lot of them. There are a lot of concepts here, and I'm not going to delve into them because most of you already know that. But the basic unit of work is the pod. It's not even the container. The pod is an abstraction over the container. And basically, you can have pods with multiple containers inside them. And multiple containers inside the same pod that can share networking and can share volumes, etc. And then we have further abstraction over this basic concept. For example, we have deployments. Deployments basically abstract over having multiple replicas of the same pod. This is because the pod usually is intended, not usually, it's always intended as very ephemeral. So if a pod fails, Kubernetes will automatically schedule another one, another identical one. So this assumes that, for instance, the pod are stateless. So we have stateful set, which are for stateful workloads, where each pod has to have a network identity, and they have an order. And we have jobs, daemon sets. We have endpoints, ingress, and services that are for exposing your workloads to the network, and configuration resources, and everything is basically is a YAML file, and this can get very problematic very soon, because as you can see here, there's quite a lot of YAML to write when you just want. This is a simple deployment of my previous Hello World example. This is just for one image, one pod, one image, very simple, and it's a lot of YAML. And this is, for example, a service that exposes that image on port 80, and you're gonna see later how to solve it. But the takeaway I want to if anyone to take here is that it's doable. Often we see, I personally saw in Twitter that on Twitter people often rage about Kubernetes being overkill for anyone who is not Google, who is not working on very large scale projects or planetary projects, planetary scale projects, etc. And this is not really the case. I'm going to show you that Kubernetes is actually very viable even for very low traffic workloads. And what gives you in exchange of this very high cognitive load is an excellent documentation. So it's you can achieve you can get the knowledge requested to at least have your workloads inside Kubernetes. There are plenty of resources, and the community is very vibrant. It's basically a buzzword nowadays, Kubernetes. Everybody is talking about Kubernetes, me included. And so let's see if we have our cluster ready. So I'm going to change the context to Jofra Hello World. Okay, this is my context for interacting with kubectl, which is a command line tool written in Go to interact with the API. And I can issue commands like get nodes, and it will return me the available nodes. And in this case, it's just one. I don't remember why I did say count 2, but it's just one node, whatever. And we can start deploying, we can deploy our previously built application right away by creating one. For instance, we can create a deployment called the Hello World, and we can use as image the URL of the image that I built. And I'm gonna copy paste real quick from here. Okay. Exactly. So what this is going to do behind the scene is to automatically create a bunch of workloads. We have a deployment and a pod, and once we actually have an error image pull back off because I didn't specify a tag, so I probably won't master. I'm gonna have to update it, and you can even edit your workloads once deployed. with an editor, and you can actually edit the YAML representation of the resource. So I'm going to put the tag here, and once I quit the editor and write, it's gonna automatically deploy the updated version. I hope. No, I didn't get it. Okay. Yeah. Why? Why Vim? Okay, let's do something. And let's create it again. Okay. And okay, let's see if we have the pod running. Container creating. So it's gonna pull the image from the registry and run it. Let's watch this command. Okay, it's running. So we should be able to port forward to it. To the port, local port 8000. And we have hello world deployed to Kubernetes. So I'm gonna kill the port forwarding for now. So as I was saying, dealing with the YAML can become a problem. So this is where Helm comes into place. So Helm is a tool developed by Days, which had been dealing. It's a company that had been dealing with container orchestration even before Kubernetes was donated to the Cloud Native Computing Foundation, and developed it along with Google. And it's basically I like to call it Kubernetes on steroids because it augments what you can do with Kubernetes, and it has quite a few usages and use cases. It's a package manager, so you can package whole stacks of Kubernetes applications, and even relate them in a deep, like basically a package manager like NPM. And it's also a template engine, so you can basically render a whole set of YAML manifests corresponding to a whole bunch of Kubernetes resources, and you can template them using the Golang templating engine. And it's also a release tool because it allows you to keep track of what version of what set of templates you are deploying to the server, to the cluster. And it has a few concepts. It has the concept of the chart, which is a bundle of the application itself. It's yet another YAML file, but it's way smaller than usual, and it declares a bunch of metadata about the application. Then there are releases. Releases are basically instances of a chart running somewhere. Then there is the Helm CLI, which is yet another tool written in Golang that you can just download from a binary release. And it's a gRPC client that interacts with its server counterpart, which is called Tiller, which runs and has to be installed in your server, in your cluster. And the relation of these two tools is basically that Helm CLI allows you to create charts and develop them, and Tiller manages the releases of these charts. So basically, what you have is you ask Tiller to install a chart in the server, and Tiller will communicate inside the cluster itself with the API server and see that all the resources are properly configured, and also keep track of the configuration of that stack. So as I said, maybe we have a little time to make a little demo. We won't be able to probably to show the actual continuous deployment at this point, but I'll do what I can. So the first thing we need to do, and this is a bit of boilerplate, and it's to create a role for the tiller server, because usually with Kubernetes as a service deployments, they are all almost always they have the authentication model enabled, which is a role-based authentication, and so you need to have a role for the tiller service. So just for reference, this role is a very small YAML file that it's gonna be very trivial. It's I'm gonna show you just real quick. And this is the YAML file. It's a very small YAML file. Well, it's YAML, so it's still like 18 lines for just a small role. But you can, once you have prepared it, you can use kubectl create -f and create it from a file. So this has the tiller service account created, and it's role-based authentication bound. And once we do this, we can use the Helm CLI to install the tiller server itself. So we can just call init and tell him what service account to use. And this has done a bunch of things in the kubesystem namespace. Which is installing a deployment of the tiller server, as we can see here. The Kubernetes has this concept of namespaces, which is what I was referring before as the soft multi-tenancy. So you can have this concept to separate the various resources. And usually cluster-wide components go into the kubesystem namespace. Once we have tiller installed, we can start installing charts. So charts are like packages, like an apt-get package or a node npm package. So you can just install them by referring them to their canonical name. So for instance, we can install Nginx. If we had an Nginx, we don't have an Nginx. So let's just you can use the Helm CLI again to develop charts. So we can just create a chart with like test chart. Let's call it test chart. And what it's going to do is to create a bunch of boilerplate for you. And there is the chart file, which is the metadata I was referring before, which has a name, a version, and an app version, a chart version, and an application version, which are a different thing, because you could have the same application being deployed with a different chart, an updated chart, maybe with some optimizations. And so this is basically your chart manifest. And then we have the templates, and the templates are YAML with Go templates in it. So you see these mustache-like template tags. This is basically what allows you to abstract from the YAML apocalypse that we was seeing before, and have a bunch of YAML that doesn't really change that much, and have only the relevant parts of the YAML that you want to change abstracted in some tags. And these tags are then handled via the values file, and the values file is just yet another YAML, but it has your own. Here you can give your own semantics. You can define your values file, and this acts as your API for configuring the charts. So in this case, the default chart is giving me a bunch of keys that I can change. I can change the repository image. I can change the replica count. So this involves the deployment resource. I can change the service type. So this involves the service resource. So these are different templates that are managed from a single entry point. And if you see, there are quite a few production ready charts already in the wild. I'm going to show you some. This is the official repository where they are stored. And these are all production ready. And usually they work out of the box. One of the convention of when developing Helm charts is that if you do Helm install name of the charts, it has to work out of the box. So it shouldn't require further configuration unless you want to do some customization. And for instance, if I get the GitLab CLI charts, as you can see, this one is not really that interesting actually. Let's see the InfluxDB charts. Let's see. So it doesn't have much to configure, I guess. It has some configuration related to the persistence, some for the users. You can change the resources allocated for the whole stack. It has, and this is one of the actually smallest I ever seen. If you see a user-facing application like I don't know, let's get WordPress, because why not? So usually they expose in the README the configuration that you can do with the chart. So in this case, you can even operate on the database that is going to be deployed along your deployment of the application itself. And usually charts have a lot of values that you can change, and you can even inject your own YAML into these values, so you can add your own custom annotations or custom configurations. And it is a very flexible, very powerful tool, but if used correctly, it can abstract away a lot of complexity that goes from basically having to otherwise copy-paste YAML everywhere. And YAML that is usually fixed. Now, there are alternatives to YAML, and just to get to a quick conclusion, and it all basically revolves around templating the Kubernetes manifest files, because having just YAML, pure YAML, raw YAML, it gets unmanageable very quickly. And so I wanted to just deploy a chart. There are a few charts that are for enhancing your cluster. For instance, one chart that you probably going to want to use is one that can automatically configure your DNS server for you. So every time you configure, you deploy some application, the DNS for that application are automatically added to your domain service provider. And this is provided by a chart that is called external, by a Kubernetes application that is called external DNS, and it has a chart for it. And this is your example of installing a kubesystem component, which is external DNS. And in this case, I can configure it from the CLI. This is actually setting values of the configuration of the chart from the CLI. So you can see that you can easily programmatically change how you deploy applications via a CLI and environment variables API, rather than having to edit YAML file and commit them. So in this case, I'm just going to install it. And as you can see, Helm immediately gives me all the resources that he has configured for that deployment, and then you can just query the status of it. And it will show you the status of the pods, the status of the ingresses, the status of the controllers, etc. And once we have this tool, for instance, and I think we still have the hello world deployment. Yep, it's running. So with the external DNS, we can use annotations, which are special tags inside the Kubernetes manifest files. For instance, in this case, I can use kubectl to add an annotation to an existing resource. In this case, it was hello world. And now I want to add this annotation, which gives a domain name, a host name, to an existing service. And the external DNS component that has been installed inside the Kubernetes cluster is going to monitor for this kind of changes. And it will pick up the new annotation and configure your DNS server accordingly. So let's try, I think that exists already, so let's try this. It doesn't exist. Maybe I don't have a service. Nope. So I need to create a service first. So we can expose it via load balancer, for instance. And this basically creates a service resource inside the Kubernetes cluster of type load balancer. And the type load balancer means that it will interact with the DigitalOcean, in this case, because it's on DigitalOcean infrastructure, its API, and create a load balancer for you, an edge load balancer. And once we have the service, we can annotate it. And this will add a domain name to that load balancer. So programmatically, I can configure the whole stack from the edge to my container. Now, I don't know if this is going to work, because usually domain propagation can take some time. In fact, let's see if Google knows better. Nope, not even Google. But if you go to the DigitalOcean control panel, is the internet working? I don't know. By the way, I will show you that it has configured a domain name service, a domain name record inside the configuration of my DigitalOcean account. And that will eventually expose the container via the domain service. And that's all I got. I'm sorry I can show you completely the demo, but I think we're short of time.